Good morning. My name is Tony. Um, I am a PhD researcher at UTS, and I've been an associate PhD researcher with the Australian Cobotics Centre. I'm now a lecturer at UTS as well, and my research has been mainly focused on XR and human-robot interaction for teleoperation. So this talk today will mostly be like 90% similar to my candidate assessment for my PhD. It'll be a summary of what I've worked on for my PhD. So if you're from UTS and you've listened to me before, this will be very familiar. Or if you're not familiar with the work, then I hope that you enjoy it and get something out of it. Few robots, they are really cool. And they are going into these dynamic environments to perform the tasks that we humans do not want to do. Anything that's dirty, dangerous, or dull. And they're also quite untouchable, literally. So when they're in the field doing their thing, most of the time, some sort of human input is still required as they're not fully autonomous. And most of the time, it will come in some form of teleoperation or at different levels, like either directly controlling the robots or giving them more strategic commands. But since they are in the field, in the wild, we can't really be next to them because it's their whole point. And so, and they're often in complex environments where it's hard to make assumptions about their surroundings, making for autonomy even more challenging as well. So that's why we need human-robot collaboration in these scenarios. So here are a few examples of some of my favorite field robots. The Mars rovers from NASA, of course, are insanely cool in a different planet. And some of the robots that we've made at the Robotics Institute at UTS as well, that has gone into inside the Sydney Harbour Bridge or inside sewers for inspections. And on the right is the Halo robot performing rock scaling. So that's the project that I worked on for 2 years as part of my PhD journey as well. And so you see that rock scaling robot come up a lot in some of the examples that I'll be giving in this talk. So currently most robot interfaces use 2D screens. For example, this teach pendant, that's pretty standard for cobots. While functional, these interfaces can be cognitively demanding. And for cobots, especially when they are co-located with us, physical human-robot interaction can be quite effective, as the cobots are safe to be touched and move around. This contact between human and robot can become the medium for interaction. And it's quite a quite intuitive way to control a robot. And also for co-located robots, augmented reality technologies have been used to further enhance the feedback from the robot to the user, because AR allows us to overlay virtual elements in a 3D context and improving various tasks such as collision detection or waypoint settings. And in research and in industry, it has been used extensively to enhance local HRI. But there's still a gap between co-located robot and remote robots, as when a robot is not next to you, there's a lot of challenges in visualization and user input. So people have tried various things. So this example here is a quite common technique for VR teleoperated robots. You can build a control room with different input, just as cameras or pose of the robot that is streamed back to the user. Or for humanoids-like robots with 2 arms and a head, one common technique is just to directly stream the human input, their hand pose and head pose directly to the robot, and then stream back the camera feed as if the human is the robot. In this sort of setup, latency and the mapping is quite crucial for an effective teleoperation experience. And then people have also tried different mixed techniques as well, combining point clouds and 2D cameras and interfaces to control remote robot. But there's still quite a gap between a co-located robot and remote robot, which brings us to sort of the central question of my research is, can the experience of interacting with a co-located robot be meaningfully replicated in remote robot teleoperation? And to achieve this, we need to authentically recreate the remote environment and provide feedback for the user. So with XR alone, we can already enhance local interaction with virtual elements, and we can leverage users' visual spatial and proprioceptive abilities. So your movement in 3D space is mapped directly to your movement in the virtual space, and you can perform tasks more effectively. But with a remote interaction scenario, it poses a different kind of challenge as well. And to sort of answer this question, I'm using the concept of presence, which is the subjective feeling of being in a different place than where you are, to evaluate the XR interaction designs. So presence is built on a few illusions, so place, plausibility, and embodiment. So with place especially is a hard illusion to create because we are trying to recreate this remote dynamic changing environment in real time for the user. And then with plausibility, it's the ability for the user to interact with the virtual environments with natural interactions that match the real world expectations of how things should work and should operate. So to further break down this question, my work involves these key steps. So firstly, I want to answer the question of whether using an XR interface over a 2D interface is feasible and what's the best way to do it. And then I wanted to investigate techniques to create a real-time remote scene digital twin for the user, and develop methods to facilitate intuitive cyber-physical interactions that is inspired by local interactions, and then trying to deploy in the real world to see if it actually works in the field settings. Okay, so let's go over to the first point, which is using XR over 2D interfaces actually feasible? And to achieve this, this methodology is to use a digital twin of a mobile manipulator. So I created this in Unity for testing. And it's allow users to control this mobile manipulator in VR using hand track controllers with the task designed to mimic real-world teleoperation. And within the simulated environment, we can change a lot of the settings to do user studies in a controlled setting. So in particular, I was interested in varying levels of latency. So I injected simulated latency into the simulations and see if it affected the performance. And then I also compared it with a traditional 2D interface with mouse and keyboard, with the gizmo that you can drag around and move things around. So for this task, the participants were asked to move this tool bit to a particular pose in space, and they can either visualize it through 2D screens or through a VR interface. And what we found was people using XR achieve significantly better accuracy in both position and orientation, and a significant reduction in task completion time as well. So on the graph on the right, lower is better. And As I mentioned before, I also injected latency, as well, to see how it affected the performance. And at about 1,000 milliseconds, so about a second latency, then the performance degraded significantly. But at around 500 milliseconds or so, the effects were negligible. And interestingly, we also asked participants for their subjective feedback, and they couldn't really distinguish between the 0 milliseconds or no latency to the 500 millisecond latency as well. So that tells us that at some level of latency, the system was still effective, and the user couldn't really tell subjectively, even though their performance did have an effect, but not as significant as 1,000 milliseconds. So the conclusion for this work was that XR interfaces outperform to the interfaces for teleoperation, and it set the foundation for the upcoming works, and that's what we pick XR for as the modality. Okay, so one of the crucial steps is to create a real-time remote scene digital twin. And the method that was used is to import the robot digital twin from its CAD model into the virtual environment, and then combine that with a hardware accelerated point cloud streaming method. So this is what the digital twin look like. So on the left, you can see the real robot with its real environment, and on the right is the digital twin that's reconstructed in real time. Here's the pipeline that was used. We call this reality stream. And the main concept is to stream separate color and depth images through the network that is compressed using JPEG. And then the images are then reconstructed into 3D point clouds on the VR side. And there are 4 steps that are hardware accelerated, as illustrated in the figure, including combining the depth images into a 16-bit depth image, and then creating the points and then rendering the points as paths. So 4 vertices in the VR scene, and all the steps are done on a GPU. And the reason why hardware acceleration is necessary here is to maintain high enough performance for VR, because when you put on the VR headset, if the frame rate on the headset is lower than around 90 frames per second, 60 is where it's still acceptable, but anything below that, the user will start to experience motion sickness. So performance was really important. Here's what the scene looks like with the point cloud. On the right is just me in my room waving, and as I was testing this. Here's some performance metrics that we measured. So this is with 2 480p point clouds streamed, because on the rock scaling robot, on the Halo robot, we had 2 RGB cameras. And here we're comparing it with ROS Reality, which is a quite popular package used for streaming point clouds and rendering it into Unity. And here the latency measure is still pretty high, around 900 milliseconds. But as I mentioned before, it did when we did the user study comparing latency, it did have an effect on performance, but it is still within acceptable range. While we are achieving quite high performance, 121 FPS on this commercially available laptop, gaming laptop. So apart from importing the robot digital twin model and subscribing from joint states from the real robot and displaying the point cloud, there's one more step in aligning these 2 things. Obviously, if you have the model of the robot and you know where the camera is on the robot, you can assume that will stay true all the time. But most of the time, you have to perform camera calibration, extrinsic calibration anyways. especially in few settings where, with vibrations from your scenes or as a robot is doing the task, you cannot always guarantee that the camera is going to stay exactly where you expect it to stay. So in lab conditions, you can use something like fiducial markers, like these Aruku tags or QR codes, to calibrate a depth camera to your robot. But in a few settings, for example, this is the Halo robot. Well, it was on a mine site, completely unreachable on a 30 meters high wall at an open pit mine. Then you can't really put a QR code and marker and have somebody there to calibrate cameras. So we had to come up with some sort of on-the-fly camera calibration using known features from the robot. So the method that was used here uses the known shape of the end effector as the known features for calibration. It's quite ad hoc. It's not a complicated algorithm at all, just detecting the box shape of the end effector to calibrate the two cameras. But the idea is, and there are more complicated techniques that you can use as well. But the idea is, in the wild, if you have some known features and known assumptions about your robot, you can use that to help calibrate cameras and align your models. And then the results on the right is you can have a calibrated scene where the point clouds and your model match and will be coherent for the operator. We also did a user study to test out this digital twin generation. So in this setup, the user control the robot to touch the center of the targets that we move around, controlled using a gamepad. And on the right, you can see the settings that we use with different kind of aid that was provided for the operator. So that's either displaying the 2D RGB images alongside the point cloud or bounding boxes to help the user locate the target. And what we found was the aid did not really help much. There was no difference in completion time or success rate, or the points that the participants were able to get. So that sort of tells us that the digital twin generation with the point cloud was sufficient, and they didn't need to rely on the 2D images to perform the task. Here are a few other example use cases of this method. So it's been applied for this 5D enabled cobot, again, with the point cloud streaming overlaying on top of the digital twin model. And this was also used at the UTSI launch event where we had participants, people at the event cut this ribbon, entirely relying on the visualization from the digital twin. Okay, so that's the information, that was the information flow from the robot, collecting information from the scene to the human. How about the other way around? How do we facilitate cyber-physical interactions in this virtual environment? And again, I was inspired by PHRI. So the goal was to emulate physical interactions and then to provide visual, audio, and haptic feedback to signify affordance. So affordance is the relationship between what an object can do and a user understanding of what it can do. And with a physical robot, with a cobot, when you grab and move it around, the fact that you can feel whether it starts to move with your movement tells you whether it's movable or not. If it resists it, then you know that the robot cannot afford that movement. But how do we replicate that in the virtual space? So in VR interaction or in the virtual environment, this sort of distance grab is quite popular. If you played any VR games or if you interacted with the XR system before, and you know this very well. So you can point at something with your controllers or your hands, or reach it directly and grab and move it around. And with a robot, what we have designed is, depending on where you point and grab at the robot's body, so it will react differently. And there will be some visual feedback, so it will get highlighted, and some audio cues will play as well to tell you that, yes, you can start interacting with the robot in this way. So if you grab the links, then the system will know that you're trying to jog the robot's joints, and the visualization will show you the subsequent links from that joint that you are controlling. So you're sort of seeing the future path of the robot. And similarly, for something like the end effector, then we can perform post tracking or position-based solving, and we have a planner that's using Move It to control the robot. So that's the different interfaces. And in both of these setups, we are controlling robots using from exocentric perspective. So you are looking directly at the robot as if you're looking at a physical robot. But in the virtual environment, you can also have an egocentric perspective, and this is quite useful for like humanoid or human-like robots again. And when you align yourself in the virtual environment with the robot, you using the same interface, you can get this bimanual control, human mimicking results. Okay, so we did another set of user studies to see how well it performs compared to PHI for a co-located robot. So in this user study, with the PHI interface, the robot has an admittance controller. So the end effector is simulating a mass spring damper system. And as the user grab the end effector and move it around, it will move accordingly using a force torque sensor that's at the end effector of the robot. And to sort of isolate just the user input and not caring about the visual feedback, we're using pass-through. So this is done with a mixed reality headset. And this pass-through view is sort of like the perfect setup for visualization, where you can still see the robot in front of you. Even though technically it's not perfect like our eyesight, but this pass-through is good enough to approximate that. So that helps us just isolate the interaction itself and not the visualization. And for this particular task, we asked participants to place foam blocks on top of each other. And we measure completion time, success rate, and there was some questionnaires at the end to measure subjective measurements as well. And the results were that PHI still performed better. The success rate was the same, but users performed the task quicker, basically grabbing the robot. But interestingly, looking at the subjective measurements, people felt that the physical demand of PHI was higher, whereas the mental demand of the XR interface was higher. But people did feel safer using an XR interface interacting with a cobot than physically touching it. I guess that's just from the fact that they're more distance from the robot instead of having to touch it, and maybe they're worried about the robot acting weird and hitting them. But other than these three factors, then the other four that we measured was basically the same between the two interfaces. Within the same use study, we did a different set of settings to detect whether presence have any influence on performance for a remotely teleoperated robot. And for that, we used the digital twin point cloud generation that I mentioned earlier. And we vary the settings of whether the user can see the real environment around them or not. And they did the same task. And for measuring the sense of presence, 14 pairwise comparison questions from the iGroup present questionnaires was used. And within this questionnaire, it will be grouped into different categories for measuring presence. So there was no difference in performance between the two interfaces. And subjectively, people felt that when they could not see the real world surrounding, when the background is black, then the task was more involved. So that's the first subjective measurements on the left there. And they also felt that the spatial presence was higher. Looking at the presence to performance correlation, something quite interesting appeared. So my assumption in the beginning, my hypothesis from the beginning was that if people felt more present in the virtual environment, then their task performance would be better. But what we found was quite the opposite of that. Even though the fit line here for the correlation is not statistically strong, the p-value is at 0.059. It's pretty close. What we actually found was, as the people felt more involved in the virtual environment, they actually took more time to complete the task, which is the worst performance because they were told to do the task as quickly as possible. So I guess this is partly because when they could see their real environment around them, their movement in 3D space as they complete the task was freer because they can see that they're not going to bump into any real world objects. Whereas if they're completely immersed in the virtual space without any visual from their surrounding, then they're more careful as they do the task. And that's why they took longer. And this is the same for spatial presence as well. Okay, so those are the findings in lab settings, but does it work in the real world settings? So that's where the Halo robot and the rock scaling robot come in. If you're unfamiliar with mining and rock scaling, it's a task where every once in a while they have to send people to abseil with ropes. They are called rope access technicians. They abseil with ropes to clear away loose rocks on the wall that have potential of falling off and causing injuries and damages at the mine site. And this is done manually, and it's a very hazardous and dangerous job. So at UTS, we produce this prototype mobile platform to go over the wall, and it can be teleoperated by an operator in the safe distance away from the wall. This is the setup that we use on site. So everything's still wired through a local network, but the operator is located in the control station on the bench as the robot goes over the pit wall. And all the visualization feedback and control modes was implemented, as I mentioned before. And this system was deployed and was operational on a real mine site in Western Australia. One of the key, and on the graph on the right, we're measuring people's attempt at moving the robot to a particular pose in space, and we can see that there's a learning effect over time as the users familiarize themselves with the systems, and these users were mine technicians with no experience with the robot or XR as a whole. But still, one of the key insights that we learned from this was that on the interface, switching between different views. So we also had a fisheye camera that you can see on the left there, providing an overview angle. And then apart from the point cloud from the two RGBD cameras, there was also just flat RGB view from the cameras as well. And allowing users to switch between these methods was necessary. They asked for it. And most of the time, they will rely on this visualization for bigger movements. And when they actually need to get to a particular difficult spots, then they will switch to the digital twin and the point cloud for this finer 3D manipulation. So allowing people to switch between different modalities is necessary. Okay, so to quickly summarize, so far we know that XR is significantly better than 2D interfaces for 3D manipulation tasks, and using simulations are very useful to control your user studies. This optimized point cloud real-time steam digital twin generation is comparable to a line of sight for a specific task. However, higher presence might not necessarily mean better task performance. Cyber-physical interactions can be designed to effectively emulate physical interactions, again, inspired by PHRI, and this framework can be used in real-world settings. And giving the end users flexibility in configuring their setup is ultimately always the right choice. So to go back to the research question, can the experience of interacting with a co-located robot be replicated in remote teleoperation? Maybe, we're pretty close. But what more can we do? So some of the limitations with the current setup is with haptics feedback. So spawning from this work, I've further investigated using force feedback, which led to some of the collaboration with some of the other ACC members, with Daniel and Dylan. And the point cloud rendering still has a bottleneck at higher resolution of the point cloud. And there are better scene generation techniques. At the bottom here is just me playing around with Gaussian splats, which is quite trendy recently, but that cannot be in real time yet. It's other limitation, but there are other better techniques that can be investigated for digital twin, real-time digital twin creation. And collaborative teleoperation can also be implemented. And ultimately, moving beyond teleoperation, if you can track the human data as the humans doing the task, then potentially we can look at human skill transfer and training some AI models to transfer the task of the human to a robot instead of manually controlling it. And also going beyond emulating physical interactions is some of my current other work in collaboration with other ACC members. Within XR, especially in mixed reality, you can show information that you cannot show in real life in physical space, such as the robot's unreachable regions in 3D space, or have some sort of other methods of controlling robot, like drawing in 3D space and having the robot follow your planned trajectory. So these are some of other methods of visualizing information from the robot, cobot especially, and then programming it more intuitively using XR. Okay, that's the end of my talk. Here's an open call for collaboration. So at the moment, I'm in the process of releasing all that work as a package called XR-Vis, the Unity-based MetaQuest native. So it can be installed on your headset as like an RVis alternative but in XR. So it's called XR-Vis for us too. It's not fully released yet because I have to fix up all my spaghetti code. But if you want to try a version, then feel free to contact me for it. And thank you very much for listening.
Wow, that was fantastic. Really fascinating work. Thank you so much for sharing that with us today. I am wondering if anybody has any questions for Tony. We've got a few minutes that I'm just looking to see in the chat if anybody has any questions, or you can go ahead and ask any questions you might have. Let's see. Oh, Nathan has a question. I see your hand up, Nathan.
Yes, I do, and I don't know how to work Zoom. Otherwise, I would have done the virtual hand. Sorry.
Hi, Nathan.
Hey, how's it going, Darren? I haven't seen you for a while, mate.
Yeah, I haven't seen you for a while. Hope you're doing well.
Oh, it depends who you ask. How much ground use you've got? So you've got a trial. Oh, let's back up. First off, that was cool. I like your presentation style. Your work's even better. Awesome.
Thank you so
I should
much.
have started with that.
Oh,
So the field stuff you've done is pretty cool, pretty impressive. What's going on next? Who else is involved? I'm just so excited. Want to try and help make something happen.
so the Halo project has ended. We've shipped the robot to them, so it's in Perth now, and we've handed over all the documentation and the interface and everything. They had plans of scaling it up, but we haven't really heard much. I'm not sure if they're doing it in the background or not, but yeah,
Who's they?
Austro.
Austria.
So
Okay.
the partner was Austro.
Yeah, cool. Okay, cool.
Yeah, like I really wanted to see it being scaled up, but we had a lot of mechanical issues. You know, the robot is way smaller than some of the mining equipments that they have there, and they will talk about potentially outsourcing it and like retrofit like an excavator or something like that of a bigger scale in order to do the task more effectively. But there's a lot of engineering work that needs to be done to scale it up, and the interfaces can still be the same or like can be replicated for anything. But yeah, it's out of my hands at the moment.
Excellent. We have a question from Jared in the chat, which I'll read out. Thanks for the presentation, Tony. What are your next immediate steps for the research now that you've completed your PhD?
Yeah, thanks for the question, Jared. I guess the immediate step is to, like I mentioned, trying to package this up and releasing it so that more people can use it and further develop and test it out. Yeah, I'm at the moment I'm really interested in what I mentioned before, the better visualizations with something like Gaussian splats or something like that, and then using Teleoperation for training for human skill transfer. So I'm sort of like I've done XR, VR, and Teleoperation for the last few years, and kind of not sick of it, but I'm trying to take it to the next step. So I'm looking for more collaborators and then share my work. Is the immediate next step. Yeah.
Excellent. Oh, let's see. That does sound very excited. Does anybody else have a question? Sarath, you turned your camera on.
I'm on the spot here. Tony, that's a great presentation. I don't think I have a question, but I think it is. I have seen this work and it is really good. And I remember I experienced that while we were launching the Robotics Institute. We cut the ribbon using that. So I think there are many applications in this one, not only in the particular domain that you are mentioning, but I think it can be expanded into many other areas where maybe a target is either training in the areas of training in a difficult environments, or it could be really working as a remote option for difficult environments. I think it's a really great job. Waiting to see your release of the package.
Yes, thank you, Sarah. I mean, it's been on the top of my list for a while, but I kept adding things to it and then was doing other things and never got around to releasing it. Even the point cloud generation, there's still more work to further improve it as well. But I wanted to put this on the slide to have it out there in the public that I'm going to release it so that people will start asking me for it. So I have the motivation to do it.
That's fantastic. The main thing is that, you know, you will not release it if you are going to fix everything, I think, because every day something will come up. So,
yeah.
yeah.
Oh, excellent. Well, there is Muge has her hand up, so Muge.
Yeah, I was just interested whether you had a chance to try this in a fully immersive environment, like a cave system, or and whether that bodily embodiment has any effect on the outcomes.
No, I haven't. Yes, there's no, like, out of the illusions of create presence, I think embodiment is the one that I didn't really touch on at all. Mostly which is the physical interaction. And I found it most useful for interacting with the co-located robot as well, with the interface alone. That was what my work recently has been more focused on. But yes, I guess it can be combined with like a immersive environment. We do have the data arena at UTS, and just but yeah, I never got around to using it. Yeah.
Okay, thank you. There's one last question that we can take. We've got 1 minute. Have you done or are you thinking about using humanoid robot as a carrier for similar questions in humanoid robot human interaction?
Yep, thanks for the question, Nikon. Yes, I'm actually I've tested this for humanoid robots as well, using the similar technique of, instead of grabbing the end effector, you grab their hand and move it around, and you stand in the virtual space where the robot is, and essentially you are the robot. So yes, I've seen it used for humanoid robots, and I've tried for humanoid robots as well. It's just not at the stage where I can share it yet, but there's a lot of potential in that area. A lot of research has been done in human skills transfer with XR for humanoid robots. Of course.
Well, I think we'll all be very excited to see where all of this goes next. There's so many applications and possibilities. Thank you so much, Tony. Really appreciate sharing everything that you've done, and hope everything continues to go well for you. And yeah, we'll be looking forward to hearing and trying out the tools that you've made. So thank you for sharing all of that.
Yeah, thank you very much for having me.
Thanks, everyone. Have a great day. See you.